In the famous words of Nabon, the Dean of Iteration, again. Anywhere. But if you have this down, that unit circle is easy peasy.
Celebration next Thursday, the 27th in the gym. Program begins at 7. $5 for parents and guests, complimentary for all. Find out student conversation that have been missed. Monday, freshman impact program day all day in the school and in the parking lot. All freshmen Tuesday park and report stations at 8:15. Reminder to all students that parking will be limited on Monday to the north portion of the main lot and the northwest lot. Make sure you plan accordingly, as parking spots will be at a premium. Sunday coordinates for Monday. All please stand for the pledge. Please, the flag.
The United States of America, and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
All have a great day.
Don't expect a 30-second speed run of it, but 2 minutes? Okay, we should know these. Who else? Any of you on the freshman impact list? Okay. Be continuing to 4-4 on Monday. And it's brand spanking new. I don't know if your Algebra 2 teacher showed you conic sections or sinusoidal functions at all, sine cosine waves. I know we didn't get to it. Graphing plus fractions plus terms of pi radians. Okay. We'll start into it today. But Monday will be the meat and potatoes of it. Doing stuff like phase shift plus change to periods. So I've got last year's is already linked in plan book. So I take that back. I think. Because I know last semester I started going back and nuking old videos just to clean up my YouTube. So the link in Planbook might be off, but if you just go to the channel and to one of the old, like, they'll say like F22 or S22 PreCalc, if you go back into one of those old playlists, there'll be one. Okay. Wake up, Frank. Start with the easy of the easy, 1, 1 square root of 2 on a 45, 45, 90 triangle. If I know that 45 degrees is the angle at both of the complementary corners, so they both have isosceles, right triangle, going to have the same adjacent and opposite regardless of which angle you're looking from. Square root of 2 over 2 when rationalized. Or just regular square root of 2 if I look at the reciprocal. When the opposite and adjacent are the same, tangent and cotangent are both 1. If we switch over to a 30-degree angle, 1, 2, square root of 3. There goes breakfast. From the 30, I've got a 1/2, a square root of 3 over 2, and a root of 3 over 3 when rationalized. If you know those, everything else should fall into place from there. Their reciprocals, and then its complement, 60, you just cross over to the complementary values. Sine of one is cosine of the other. So the cosecant of one is the cosecant of the other. Cosine of one is the sine of the other. So the secant of one is the cosecant of the other. Tangent and cotangent will swap places because the opposite and adjacent have swapped. We're getting better? Okay. Now, even if you don't have it memorized, I'd like you to, but just like all the other stuff, remember banging on that drum about squares through 20, cubes through 10, fourths through 5, blah, 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 blah. I never made you memorize it. Even if you don't have all of this memorized, pink, there we go. If you know this, and not even that, if you just know this, you can fill the rest out. Okay? So we were right at the precipice of this, where we're starting to look at these. Whoop. And I believe the very next thing was the unit circle, right? So here's the idea behind it. I keep saying the unit circle. Unit means 1 unit. I'm going to force the radius to be 1. Now, yesterday, someone had a really good question in third hour, and it was the one where I had the secant of theta was square root of 3. And they said, how do you know that it's square root of 3, that it's square root of 3 here and 1 here? How do you know that that wasn't 3 over square root of 3? Right? Because if I rationalize, I'll multiply by square root of 3, and they'll cancel. How do you know it wasn't that? And I showed them that, well, if this is 3 and this is square root of 3, isn't the secant value still going to reduce down to square root of 3? If I do Pythagorean with this, 9 minus 3 is square root of 6. It's no different than if I originally had 3 minus 1 was square root of 2. Every one of those values scaled up or can scale down. The ratio remains the same. So the idea behind the unit circle is I take this triangle right here and I say, I know that these two sides are the same. I know that those are 45s. What if I made the radius 1? How would I have to change the sides? Not by half. Close. How do I go from here to here? Divide by the square root of 2? So what is 1 divided by square root of 2? Oh, should we go back to those ones? Let's take care of that first. If we struggled with those. If you're dealing with 45, 45, 90, and I'm dealing with 1, 1 square root of 2 normally, which I would call leg hypotenuse. This is what I used to do in my geometry classes. I'd have kids say, if I'm going from a leg to a hypotenuse, multiply by square root of 2. If I'm going hypotenuse to leg, divide by square root of 2. I just had them write those out so they didn't have to kind of reinvent the wheel in their head every time. 30, 60, 90s. Thirty, 60, 90, 1, 2, square root of 3, and we labeled them as the short leg, the long leg, and the hypotenuse. And said if I go from the short leg to the hypotenuse, multiply by 2. If I go from the short leg to the long leg, multiply by root of 3. If I go from the long leg to the short leg, you divide by root of 3. If I go from the long leg to the hypotenuse, it's usually more conventional to make a pit stop at the short one and then multiply by 2, because you'll divide it by root of 3 and then double it. So long to hypotenuse was times 2 over root of 3. Hypotenuse to short leg, I divide by 2. and hypotenuse to long leg, I would divide it by 2 and then multiply by root of 3, so I'd say times root of 3 over 2. Okay, so all this from back in geometry. And I apologize in these first couple of sections. I know that I have been, not just due to sleep deprivation, but I've been grumbly about it, and it's because it is not normal to slow down like this in PreCalc, but it sounds like y'all just basically didn't have geometry, or part of geometry, because of a poor student-teacher experience, okay? That ain't on you. We're just picking up the pieces now, okay? You're still going to get the information. All right, so if I use that, I can just do it right here. What changes when I say, nah, this is going to be 1? How do I fill out the other 2? How do I fill out the legs? Going from hypotenuse to leg, I have to divide by root of 2. We said we're going to divide by root of 2, so I have to rationalize square root of 2 over 2. That's on a unit circle. The radius is 1 unit. And you're like, okay, root of 2 over 2, yeah, I've seen that number before. If I turn this to a 1, what colors am I not using yet? Blood red. If I turn that to a 1, to go to the short leg, what? To go from the short leg to the long leg? Look at what you just did to start the class. You were doing the special trig ratios of 30, 45, and 60. What's the sine of 30? The sine of 30 is 1/2. What was sine in terms of my x, y, r shortcuts? Sine uses opposite. Sine had a y value, y over r. What's the cosine of 30? Cosine used what with r in our x, y, r shortcuts? What's the sine of 45? And sine used y. The cosine of 45 was square root of 2 over 2 and used x. When I switch to the unit circle, 1 unit radius, that means x over r, y over r is always thing over 1, which is itself. When I switch to a unit circle, my x and y values are now the cosine and sine values of that angle, because they use the adjacent and the opposite values. Here it comes. Where's Big Papa? There we go. First, Here it comes. Go. At 30 degrees, what's the sine value? At 30 degrees, what's the cosine value? Who else has a reference angle of 30 degrees? 30 degrees off the axis. Where's 30 degrees off the axis? So over at 150, I'm going to fill this in with all the pretty colors later. The sine value of 30 is still 1/2. The cosine value of 30 is still square root of 3 over 2. Yes. We're going to write the angles all the way around. Angles in degrees and in radians. Okay. Who else has a reference angle of 30 degrees? (210) does. The sine is 1/2. The cosine is square root of 3 over 2. 330 does. The sine is 1/2. The cosine is square root of 3 over 2. But all students take calculus. In quadrant 1, sine and cosine are both positive. In quadrant 2, only sine is positive, which means the cosine is negative. Look in this quadrant. Isn't that now a negative positive coordinate? In quadrant 3, only tangent is positive. The other two are negative. Isn't this now a negative coordinate in quadrant 3? If I go over to quadrant 4, only cosine is positive. The sine will be negative. This is now a positive negative coordinate. You don't have to memorize the entire unit circle. You just got to know your trig ratios, and then all students take calculus. And just puke all the numbers in there. The unit circle is something you have already been doing. We're just going to put it all in one place. Okay? This is why we've been banging on that drum about the special right triangles, about the reference angles, about if I know this, if I know these two triangles, I know everything. And that's also why it's one of the few things that I say you actually got to know this. So, let's start by getting all our angles on there, all the way around. Let's go degrees. We start at 0, we end at 360. All the way around the block, what do we got? 30, 45, 60, 90, 120, 135, 150, 180. We seem to do good with quadrants 1 and 2. How are you downstairs? 210, 225, 240, 270. I would do it in 30-degree chunks, and then the middle is my 45 chunk. Add 30, add 30. The middle is my 45 chunk. Okay? In terms of radians, we start with 0 radians, we end at 2 pi. See that other dashed line on there? If this is 2 pi, then this is pi. So what are the 90 and 270 respectively? Pi over 2 and 3 pi over 2. Then cut all of those in half. Go by your pi over 4 increments. We go to 1 pi over 4 in the middle. 3 pi over 4 in the middle. 5 pi over 4 in the middle. 7 pi over 4 in the middle. Because 2 pi over 4, 4 pi over 4, 6 pi over 4, and 8 pi over 4 are already there and simplified. Now do your 30-degree increments. In terms of 30 degrees is how many radians? Pi over 6. So I'm going to count in sixths. I hate that word. Like, seriously, who decided to put that many consonants together? Tell you what, they weren't French, because they love vowels. Oh God, me and Minnie have been going back and forth for 8 years now. And she's like, yeah, math, numbers, I'm smart. We just, yeah. Pi over 6, and then a 2 pi over 6 is a 3 pi over 6, already there. A 4 pi over 6. A 5 pi over 6. 6 pi over 6, already there reduced. 7 pi over 6. 8 pi over 6, reduce it. 9 pi over 6, there and reduced. 10 pi over 6, reduce it. And 11 pi over 6. Okay. Next to this, I would like you to write that every one of your coordinates is going to be, I want to get my colors right here, cosine theta sine theta. Every one of these coordinates all the way around is cosine comma sine. So if you know those trig ratios, you are good to go. I'm already in orange. Let's do the sine stuff. What is the sine of 30? Now before I go do the rest, don't draw this part. It's reference angle, it's reference angle, it's reference angle. They all are going to share the same lateral and horizontal, the same horizontal and vertical movement. So if the sine of 30 is 1/2, the absolute value of the sine of each of these is also 1/2. I'm just going to go around here at the end and change all of my signs. Okay, what about the sine of 45? Square root of 2 over 2. Again, it's reference angle, it's reference angle, it's reference angle. This is also square root of 2 over 2. This is also square root of 2 over 2. This is also square root of 2 over 2. Oop. What is the sine of 60? Now, if we're struggling with that, look at the actual triangle here in terms of a 30, 60, 90 triangle. I go over square root of 3 here, 1 here, 2 there. The sine is square root of 3 over 2. It's taller than it is wide, so it has to be root of 3 there. Go ahead. So if that's square root of 3 over 2, then its reference angle, its reference angle, its reference angle are all square root of 3 over 2. Square root of 3 over 2, square root of 3 over 2, square root of 3 over 2. Now, these are all cosine comma sine, but they're also coordinates. They are coordinates that stretch from what is the furthest left, the smallest x value on this coordinate plane? -1. It goes all the way over to -1, all the way over to 1. It goes all the way up to 1, all the way down to -1 on your quadrantal angles. So it's got this, from 1 to -1, from -1 to 1. Okay, and if I know the sine of 1, I know the cosine of its buddy, its complement. Oops, we forgot. Sine of that is 0, 0, 0, and 0 for cosine values. So if the sine of 30 was 1/2, the cosine of 60 is 1/2. Which means its reference angle, its reference angle, its reference angle are all 1/2. Because if the cosine of 60 is 1/2, then the cosine of 120 is 1/2, but it'll end up being negative because I'm in that quadrant. And this is 1/2, and this is 1/2. If the sine of 60 was square root of 3 over 2, the cosine of 30 is square root of 3 over 2. So its reference angle is. So its reference angle is. So its reference angle is. And the sine and cosine values for 45 are the same because it's a isosceles triangle. Square root of 3 over 2, 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 or square root of 2 over 2. Oops. Almost. This is the unit circle itself. I am going to put all my negatives on there. But while I'm at it, it's not part of the unit circle itself because they're not part of the coordinates, but I would also like to write the tangent values next to these so that I don't have to reinvent the wheel. See, it's annoying if I say, what is the tangent of 30? And you're thinking, well, here's x, here's y. I need to do 1/2 over square root of 3 over 2. Not many of us are going to want to rationalize our compound fractions on the fly like that. But the tangent of a 30, 60, 90 triangle has a 1 here, square root of 3 there, 2 there. As a ratio, 1 over square root of 3 is, right, because this will be 2 over root of 3, cancel, cancel, rationalize. So instead of doing all that work every time, how about I just write my tangent values next to it so I don't have to keep doing that? Yes. So, what is the tangent of 30? Root of 3 over 3. What is the tangent of 45? Uno. What is the tangent of 60? Well, if this one is root of 3 over 3, flip things around, just root of 3. If these are the tangent values, then their reference angles have the exact same things. This drops down here to its reference angle. This drops down here to its reference angle. This drops down here to its reference angle. these all shove over here or drop straight down to get the exact same thing. Square root of 3, 1, root of 3 over 3. We're getting there. They do have degrees. Remember that tangent is also opposite over adjacent, which is also y over x. So the tangent of 0 is y over x. Is y over x. Y over x. Undefined. And now, all students take calculus. Yeah. Everything's positive in this quadrant. Only sine is positive, so I will negate the cosines and the tangents. In quadrant 3, what's positive? All students take tangent. So these are all positive because my x's and y's are all double negative. Because I'm in this quadrant, and this quadrant is a bunch of x and y coordinates that are negative, negative. I'm in this quadrant, not only are x's positive and y's negative, but all students take calculus. The cosines are positive, the sines are all negative, as are my tangents. The unit circle is not this big complicated thing. It's the difference between I know this thing and I know this thing well enough to analyze it and debate it and apply it. It's the difference between I took a class on that once versus that's the last 15 years of my life. Okay? That deep dive on something, the unit circle is the holy grail of trigonometry because it takes those two triangles and just explodes them out and maps them to a coordinate plane. And you're like, all right, cool. It's also the cheat codes. That's the part we might like a little more. See, if I have this unit circle, then when I ask you, what is the sine of pi over 3? No, not you. When I ask what is the sine of pi over 3, I'm going to go to pi over 3, and sine is the y portion of the coordinate. Square root of 3 over 2. Answer. Okay. The sine of pi over 3 is square root of 3 over 2. The cosine of 45, or not 45, 135. I go to 135, I look at the x portion of the coordinate. It is negative root of 2 over 2. Tangent of 270, go down to 270, and either y over x, or if we wrote our tangent value next to it, undefined. Cosecant of 11 pi over 6. Uh-oh, this whole thing was sine, cosine, and tangent, not cosecant. But if I go to 11 pi over 6, cosecant is a reciprocal of what? Sine. So take the sine value and flip it. Negative 2. Ta-da! Answers. This is why when you get to trig, you aren't just going to get all of the notes. Because all of the answers are buried within I understand these two triangles. Fill them out. Finally getting the unit circle, understanding what it means, where it comes from. It's like, I don't know, when you hit the end of Inception and everything just kind of falls into place and connects, you're like, oh. This is why I tried pounding on those XYR shortcuts. Because if the radius is 1, then y over 1, x over 1 are always going to be the x and y, or the vertical and horizontal movement. They're going to be the coordinates. So cosine of pi over 4, I can just look up that part of the coordinate. If I know that 120 has a reference angle of 60 and the sine of 60 is square root of 3 over 2, and I'm in second quadrant, I know it's positive. Or I can just look at the y portion of the coordinate and at 120. Cotangent is a reciprocal. If 210 has a tangent value of square root of 3, reciprocal is root of 3 over 3. If 7 pi over 4 has a cosine value of square root of 2 over 2, then the reciprocal for secant is just square root of 2. And it's all right there on the unit circle. What? Oh, I said it, but I said square root of 3. I just kept writing. Dang it. Where's my marker? Okay, just the way you said that, the whole vibe. I'm a nerd, okay? There's this magic card and the art in it, and there's this gal just kind of like draped across a throne with zombies, because she's a necromancer, all like feeding her grapes and stuff, and it's just this whole entitled attitude of, feed me, mortal. Just nailed it. Yeah. Okay, so head back to that unit circle. So each of these, if I was saying, again, cotangent of 210, I go to 210, right next to it we had square root of 3 over 3. The cotangent would be, okay, I flipped that, square root of 3. The secant of, what was it, 7 pi over 4? Well, I'll go to 7 pi over 4. The cosine is square root of 2 over 2. Secant is the reciprocal. I just flip it. Everything's right here. The entire unit circle. With today's, I am also going to give you, I'll send it out on Remind just as a picture, this guy. It's got the unit circle with all of your values in degrees and radians, with all of your coordinates written out, and next to each of them, the tangent values. Next to those, this is going to be next week, are inverse trig functions.
That's not going to be on our little text, is it?
The inverse trig functions won't. But you will fill out this entire thing.
No, I mean, like, the ones we don't have.
You'll have to fill out this whole thing.
Okay.
And the special right triangles and their ratios as a chart above it. Both. Yep. That's everything is gone. Get it. Yeah. So, the inverse trig ratios, we're going to talk about that next week. Ooh. Importante. Additionally, we've also been talking about coterminal angles. If I think about, I'll come back to that. If I think about coterminal angles, go to example 8. I'll go back to the other thing later. 11 pi over 4 is too big. It's not on the unit circle itself. But here's 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8, 9, 10, 11. 11 pi over 4 is coterminal with 3 pi over 4. I can also say 11 pi over 4 minus 8 pi over 4 to get 3 pi over 4 as a coterminal angle, right? I can add and subtract iterations of 360 or 2 pi. So if I want to know what the cosine of 11 pi over 4 is, it's the exact same as the cosine of 3 pi over 4. Because the circle just repeats itself, repeats itself, repeats itself, repeats itself. I use that reference every year. That is the first time I've heard someone else pick it up. Well played. So, that is a negative root of 2 over 2. Negative 2 pi over 3. Negative means we turn clockwise 2/3 of the way to pi. What angle am I at on the unit circle? And we're back. Negative 2 pi over 3 is at, how about 4 pi over 3? We're in radians. Let's stay in radians. Come on. Keep decorum now. So this is the exact same thing as the sine of 4 pi over 3 because that's its coterminal angle. And the sine at, stop that. The sine at 4 pi over 3 is
negative. How would you know that's a coterminal angle? How would you get 4 pi over 3?
because I go 1 pi over 3, 2 pi over 3.
So take 2 pi minus.
I could also do the coterminal angle part of it is if I have negative 2 pi over 3, I'll just add 2 pi, which is 6 pi over 3, getting 4 pi over 3 as a coterminal angle. I can math it or I can visualize it. Okay? It's your choice. Because if they say negative 2 pi over 3, well then when I add 2 pi to it, I will end up at 4 pi over 3. And the sign value is the y portion of the coordinate. Now, I can still do all of these the way that we were. There's nothing wrong with drawing that, making your reference angle, knowing this is pi over 3, and then putting on there 1, square root of 3, 2, know that those are negative because I'm in quadrant 3. It's just, you don't have to, math dad joke inbound, you don't have to reinvent the wheel anymore because it's right there. All you got to do is look up the information. 19 pi over 6 is way too big. That's more than 2 pi. 2 pi would be 12 pi over 6. How much bigger is it? Go find its coterminal angle of 7 pi over 6. Look at 7 pi over 6, and I can either do y over x, or if I've already written it down, I know that the tangent value is square root of 3 over 3. I subtracted 2 pi. I found coterminal angle. No, because I'm in quadrant 3 and all students take calculus. Tangents are positive in that quadrant. Okay. The interconnectedness between all of these concepts we've been just grinding away at for 2 weeks. It's all right there in the unit circle. Okay, just look it up on the unit circle. And I strongly recommend that you have the unit circle and those trig ratios. Maybe have those on a separate sheet or a note card, or just take a picture of it somewhere on your phone. Okay? You should have that on hand so you don't have to keep flipping back and forth, or so you don't have to keep reinventing the wheel every time. In fact, I'm going to write a little note to myself here. If y'all want to come back during Spartan time, if y'all want to come back sometime after lunch, that special right triangles and the chart of the ratios with it and the whole unit circle, the quiz that you'll take without notes, I'll just print off spare copies of it ahead of time. Okay? And then you can use that as your unit circle on all future tests. Okay? No. You just got to know it.
So you can come and get those at lunch?
I said sometime after lunch. I'm not sure when I can go print them off, but within the next 2.5 hours, I'm going to try. Okay? So, the sine of 13 pi over 4 is coterminal with the sine of 5 pi over 4. And since 5 pi over 4 has a sine value of negative square root of 2 over 2, so does 13 pi over 4. I'm down in quadrant 3. Sine is negative. If I add 2 pi onto this, or 6 pi over 3, I will get the cosine of 2 pi over 3. I'll go look at the x-coordinate for 2 pi over 3, and I see that it is negative 1/2. So what?
Like, it is negative 4 pi over 3. Did it go down to that one too, or no?
No. Negative 4 pi over 3 is like this. I'm saying that if I add 2 pi, it's right here at 2 pi over 3. I subtract 2 pi, which is 8 pi over 4, getting 5 pi over 4. I'm pretty sure 13 minus 8 is 5.
Why go around 3 times? Pi is 12 pi.
Remember, 180 is 1 pi. A circle is 2 pi's. So think of it as it went around 1.5 times, then a reference angle of pi over 4. If you want to say 13 divided by 4, it was 3 1/4, right? So that's 3 calzones and 1/4 of a pi. If it went to a pi 3 times, it went 1 pi, 2 pi, 3 pi, and 1/4. That the idea that the entire circle is 2 pi's instead of 1 pi's, one circle is 2 pi's, definitely makes kids go cross-eyed sometimes. I get in my own head about that. I got a whole board to prove it. Okay, last one, tangent of 15 pi over 6, again, is too big. I'll subtract 2 pi. 2 pi is 12 pi over 6, getting tangent of 3 pi over 6, but that's tangent of pi over 2. So when I go to pi over 2 on my unit circle, I do either y over x, 1 over 0, or I have my tangent value written next to it and it says, you can't do that. So we have the options of either everything we've been doing for the last few days. Draw the triangle. What quadrant am I in? Draw the triangle, put your ratios on there. Or, now that I got the cheat codes, go look at the unit circle. Okay? Okay, so right before that, right here. So we, the grimace on Holly's face. If he's excited, it must be bad. Okay? It's really cool. Now we start to connect all the way into PreCalc back to all the way in physical science. Maybe even basic 8th grade science. See, the unit circle, if I was talking about its sign values, its sign values are the y portion of the coordinate, correct? What is the smallest that they ever go? -1, down here. And then about -0.8 something, about -0.7 something, about -0.5, and then 0, then +0.5, +0.7, +0.8, 1. And then, what does it do? It goes back down. If I were to track that progress and say, 0, -1, and 1, and I ask you, what is the sign of 0? Here's pi, here's 2 pi. Okay. The sign of 0 is 0. Whoop. What is the sign of pi over 4? Sine. Square root of 2 over 2, or about 0.7-ish. So I'll go about there. What's the sign of pi over 2? 1. What's the sign of 3 pi over 4? So about that 0.7 again. What's the sign of pi? What's the sign of 5 pi over 4? So about -0.7. What's the sign of 3 pi over 2? 7 pi over 4. 2 pi. And what happens when I keep going and now I want to go to 9 pi over 4? And then I go to every time. And yes, sir. Welcome to section 4.4. We are finally going to be graphing these things. No, this is the idea behind it. What about cosine? I've got sine right here. What about cosine? I'll just use the same graph. What's a cosine of 0? Y'all got your unit circle in front of you? 1. What's cosine of pi over 4? What's cosine of pi over 2? Oh no, all of the other stuff is in here. I'm just only doing this many. So I don't have to the whole timeline here. 3 pi over 4? Pi. 7 pi over 4. And as I continue to repeat myself and I go to 9 pi over 4. Look at what cosine does. It's the exact same pattern, but it got shifted over. Specifically, it shifted over pi over 2. The cosine shifts pi over 2 from sine because they are complements. They add up to 90. They add up to pi over 2. The cosine of one is the sine of the other. So it's a pi over 2 shift of the other graph. These are called periodic or sinusoidal functions. Periodic is something that has a period to it, meaning it will repeat itself every so many units. Sinusoidal specifically is sine and cosine graphs. It's also really fun to say. Sinusoidal. Okay? So, before I go on to this stuff, we seem to be a little bit sketchy. I want you to do those 6. Right before section 4.4. I want you to do these 6 real quick, however you want to. You want to draw the triangle and reinvent the wheel, you go ahead. You want to look at your unit circle, you go ahead. Doesn't matter to me. You take your pick. I just want you to evaluate these expressions. Some of them are on the unit circle itself. Some of them you're going to have to go find its coterminal angle. Some are going to be nice values. Some are going to be undefined. I'm exhausted. This has been a hell of a week. Check me. It has been wild. Goblin One's back at school, though. We are fever-free. (13) Cosecant is a reciprocal of sine. 1 over the sine of 90, since the sine of 90 happens to be 1. Okay, get your visualization on. Okay, if you watch me up here when I'm doing it, I'm like, look like I'm directing traffic because I'm moving my arm around to those different locations in the different quadrants. Okay? After getting another run with it, are they okay? As long as you got that unit circle, it's game on. But I would put next to every one of your unit circles the coordinate. Cosine, sine. Just so you remember that, because cosine is an x value, sine is a y value, because this involves adjacent and this involves opposite. Because in terms of coordinates, adjacent is left to right, opposite is up and down, because I keep making my triangles with the x-axis. If we have that common language, that common starting point, it allows us to have more detailed conversations. Okay? A case in point of that would be, especially in South Dakota, you may have heard regressive conversation about there's more LGBT people, there's more people who have ADHD, there's more autistic people. And then if we show you the exact same conversation from 120 years ago around left-handedness, as soon as people realize, oh wait, it's okay to be left-handed, you're not devil spawn and I don't need to beat it out of you, there was a bunch more left-handed people, and then it leveled off as a logistic graph. Because once the conversation was started, once you had the common language, it allowed more in-depth conversation. The same thing is going to happen in any aspect of life, including mathematics. Once you have the common language, once you have the common reference, you can go further past it. For example, I know it has all the information right above that, but I want you to, in this case, not look at your paper and just look up here. We analyze the crap out of every graph we have seen so far. What is the domain of this? All real numbers, because I can take the sine of any angle. What is the range? -1 to 1, because the sine value can only be between 1 and -1 because it has to be smaller than the hypotenuse or else it's not a triangle. If I wanted, x-intercepts. Okay, there's an infinite number of them, right? When do they occur? You said multiples, right? We learned in one of the very, very first lessons in this class how to write multiples in set notation. This is why I said you had to know set builder notation and interval. I would say that they are all x's such that x is multiples of what? So pi times n, because I can go positive and negative directions, and I would say that n has to be an integer. This is the beginning of section 4.4. Okay? It's all right above this. Like literally, it's in the table right above it. It's just, I want to talk about it without you just reading it. Okay? So every time I hit a multiple of pi, I'll have an x-intercept. What about y-intercept?
0.
It's a 0. Because if I say 0 equals the sine of x, The way that I solve that is with arc sine. The arc sine of 0 is 0. What angle gets me a sine value of 0? And then cosine, we're going to take this exact thing and move it over pi over 2. If they talk about extrema, notice that there's an infinite number of x-intercepts. There's also an infinite number of maximums. There's an infinite number of minimums. Tell me if this occurs here, where is that? Like as a coordinate. Pi over 2, 1. And then the next maximum occurs when? 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 1. If I back up, 1 pi over 2, 0 pi over 2, negative 1 pi over 2, negative 2 pi over 2, negative 3 pi over 2, 1. The maximums are all occurring how far apart? How far apart from here to here? From here to here? What's 5 pi over 2 minus pi over 2? Or 2 pi. That's the period. The period of a sine or cosine function, until I go messing with it, is 2 pi. Because every 2 pi, every lap around the circle, I'm going to start repeating myself. That's why we have coterminal angles. Because at pi over 6, I have this kind of information. I do a lap around the circle, and I hit 13 pi over 6. I'm going to say the same information. Corollary to history repeating itself, insert social commentary here. That period allows it to keep repeating over and over and over and over and over, and kit and calendar, kit and calendar, kit and calendar, kit and calendar. Okay. The same thing's going to go for maximums. Oh, those the maximums, since it started at pi over 2, all x's such that x is pi over 2n, n is an integer. Right? I'm at pi over 2. Oh, wait. I can't take that times n. It's pi over 2, and I'm going to keep adding 2 pi. So I need to say plus 2 pi n, where n is an integer. There's my maximums. Pi over 2, plus or minus 2 pi, plus or minus 2 pi, plus or minus 2 pi. So far, this is all decent because it's all in terms of pi and pi over 2. Those are nice fractions. They know it's going to be nice fractions. Okay. Oh, intervals of increase and decrease. There's an infinite number of them, right? It will increase from here to here. It will decrease from there to there. And then it'll repeat itself, repeat itself, repeat itself, repeat itself. That type of oscillation, a repeating pattern, is how we discovered electromagnetic radiation, is how we discovered the idea that electrons will behave in an oscillating fashion. This is how I can discover that light particles, photons, will behave like physical matter. And this leads into all the realm of physics. Okay? There's so many cool things that you can do with this. Now, if I take this exact graph, and that's at 0, 0. If I switch over to cosine, okay, there's sine compared to cosine. We already saw this. It's just a pi over 2 shift of all the same business. Okay. The first x-intercept moves over pi over 2. The first maximum moves over pi over 2. The first minimum moves over pi over 2. All of them are a pi over 2 translation because they're complements. The sine of one is the cosine of the other. So you can say all that same stuff about this, it's just you're going to have to wiggle it a little bit to match that shift. Graphing these. We are going to have translations of these. We are going to have transformations of these because back in Algebra 2, we beat the living snot out of transformations. Remember vertical compressions and stretches? Periodic functions are so special. They're so applicable in the realm of physics that they get their own words, their own terminology, where I'm not going to call this a vertical stretch and compression anymore. I'm not going to call it a vertical dilation anymore. Think back to physical science. If I go from this to this, I have changed the distance between crest and trough. It is the amplitude. A is now going to be the amplitude instead. Just like when we did the natural logarithm, a log base e, it got its own name because it was special. Now, I'm going to have a special name because these are special types of functions. Notice they do not, we used to do this in our grouping. With sine and cosine functions, we don't. And because of that, that means that C value is actually going to be a combination of my horizontal dilation and my horizontal stretch. Or sorry, my horizontal dilation and my horizontal shift. So next to this, I want you to write that the period is 2 pi over b. The period of a function, how long it takes to repeat itself. Normally, all of my sine stuff starts repeating itself at 2 pi because I'm going to take a full circle to start getting the same values again. Because that b is not separated from an x minus h, my horizontal translation is now going to be called a phase shift. And the phase shift is negative c over b. Because they don't have the x minus h, the bass-ackwards land, if you will, because they don't have it, we have to put our negative in that definition. Because they haven't separated b, I have to divide by b. My phase shift is just the horizontal translation. D, our vertical shift. Our vertical shift is always going to be in the center of these graphs, so we call it a midline. Okay. These have special names because of how special these functions are related to everything else we've done. We haven't done a periodic function before. We've never had something that infinitely repeated itself. So that's going to change things. Next to this, they have examples of what each of these do, or what some of them do anyway. The amplitude, that mid line there, that orange line, that's normal sine of x. Do you see the 0.5 and the 2 literally are just vertical stretch and compression. If I take 0 and multiply it by 1/2 or 2, it's still 0. But if I take 1 times 2 or 1/2, okay, so it's still going to have all the same x-intercepts. We saw this when we were dealing with, I kind of talked about the change in amplitude if you didn't divide by your denominator when you're doing synthetic division with polynomials. Remember, you could have had the exact same zeros, but if you didn't divide by whatever the thing was, you might have ended up with something that was half the size that it was supposed to be, because there was an amplitude change to it, because there was a multiplication factor. Same thing's going to go for reflections. If I start at 0 and normally go up, then down, and then up, and then down, and then, if I have a negative in front of it, it just means I switch which direction I'm going. Instead of starting at 0 and going up, I'll start at 0 and go down. And then continue the dance, because it's infinite. Depends whether you're talking about sine or cosine. Because if I reflect this over here, a horizontal reflection is the same as a vertical reflection for sine until I translate it. Remember us talking about you have to say reflections first before translations? It matters, okay? So when you're dealing with the parent function like this, yes, they will be the same. With cosine, it's a whole different critter. So, we don't got a lot of time, but we got enough time to do a few. Happy joy, happy joy. Yes, happy joy. Y is the sine of x. We're also going to do y is 1/4 sine of x. Look at the directions. They said to graph sine of x and 1/4 sine of x on the same pair of axes. So, what I'm going to start with is labeling my graph axes. There is no horizontal shift. There's no B and C values here. I haven't changed the period at all. So that means I will still start with 0 in the middle and the period of a sine function. The time it takes to repeat itself is still, what? I'm going to do a negative and positive iteration of this graph. Instead of going from 0 to 4 pi, I'm going to go negative 2 pi to 2 pi. 0 to 2 pi. 0 to negative 2 pi. This will show 2 periods of the function. Okay? Now, look back at the original. When did the maximums and minimums occur? The maximums, minimums, and x-intercepts, they were always how far apart? Not 2 pi. Pi over 2, right? They happened at the quadrantal angles. The relevant features of this thing will always happen at 1/4 of its period. So that's why there's 4 boxes here. I'm going to put pi in the middle, pi over 2 here, 3 pi over 2 here. Now we're going to go messing with the period next week. But for now, they're all going to have this baseline of negative pi over 2, negative 2 pi over 2 is pi, negative 3 pi over 2, negative 4 pi over 2 is negative 2 pi. Which of these two has a larger amplitude? The A value in front of it. 1, okay? Now I'm going to change these axes so that I don't have to have a really skinny one. I'm going to say that 1 is right here and negative 1 is right here. That way, that box in the middle is what? 1/2, which means if I just toss 2 little tick marks on there, in between boxes, those are now worth what? 1/4. So, sine of x. What is the sine of 0? Boop. What's the sine of pi over 2? If you need that unit circle in front of you, go for it. Sine of pi over 2. Uno! So I make a dot. The sine of pi. 0. The sine of 3 pi over 2. -1. The sine of 2 pi. 0. The sine of, okay, now go the other direction around the circle. Starting over at 0, go down to -pi over 2. What's the sine value? -1. 0, 1, 0. And then I connect the dots and say my graph looky like this. Now, I don't need to label all the other stuff because my axes are labeled, because I know it ping pongs between -1 and 1. Yeah, I mean, yeah. I never really do just because I'm lazy, but yeah. 1/4 sine of x. What's the sine of 0? Times 1/4 is still 0. What is the sine of pi over 2? 1 times 1/4 is 1/4. The sine of 0 is 0, times 1/4 is still 0. -1 times 1/4 is -1/4. 0 times 1/4 is still 0. And what you're going to get as you start to graph these is it's this little dance. It goes middle down, middle up, middle down, middle up, middle. Yes, you throw it on auto tune, you'll make millions because you're just repeating the same thing over and over and over. Connect the dots. As you are connecting these, please, 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 just like our polynomials, try to keep them curvy. Okay? It should look like a wave. It should not look like my heart monitor when my kid screams. Okay? Try to keep them curvy. These look really cool. When you put 2, 3 of them on the same axes, it's going to look really smart math. Y'all, it's not that bad. It's just up, middle, down, middle, up, middle, down, middle. Okay? It's going to look cool, though. That's a good place to pick up Monday.
I think we should have homework for the tutorial. Probably should.
Oh, well, if you have something for one person, you should share with everyone, right? So I should make sure that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 problems. We're also missing 2, 13, 14. We'll do 14 problems in honor of Lori's birthday.
Thank you.
And what if we each had one problem? Yeah, that's so Or we each had like
Someone asked about the quiz. Because this week was weird, you had your quiz on Tuesday. Yesterday was day 1, today was day 2. Monday, Tuesday, Wednesday, Thursday. Also, I put the calendar in the back. You are orange. The unit circle quiz, I'll probably do Tuesday, because then you'll have a few days to stare at it and work with it. Okay? Probably Tuesday. So, good stuff, Mater.